Example 16.3 is going to be a combination and composition problem where we're trying to take two functions and combine them together to make a new function. We have f given to us. F is given by the equation x plus 3 over x minus 4, and it has a domain restriction of 4. And g is also given to us by x plus 1 over x, with a domain restriction of 0. And we have 5 things that we're trying to define in this problem: f plus g, f minus g, f times g, f divided by g, and f composed with g. Let's start with f plus g. So I need to come up with an equation for f of x plus g of x. And we'll just take our representations that we have. That'll be x plus 3 over x minus 4 plus x plus 1 over x. And in order for us to be able to add them together, we have to have the common denominator. I will multiply f of x by x over x, multiply g of x by x minus 4 over x minus 4. So multiplying for f of x with the x times x over x, I'll have x squared plus 3x, because I'm actually going to do the distribution there. In the denominator, I'm not going to distribute, and I'm just going to write it as x times x minus 4. And then on the g of x, when I multiply top and bottom by x minus 4, I'll have x squared minus 3x minus 4, all divided by x times x minus 4. So again, I perform the distribution in the numerator, but I just leave it in factored form in the denominator. And now they have common denominators. We'll add them together by combining like terms. So we'll have x squared plus x squared to get 2x squared, 3x plus negative 3x, which is not going to have any x's, and then I just have that minus 4 there. So we'll put 2x squared minus 4 all over x times x minus 4. And there we go. That is f plus g. Now for f minus g, we're going to be able to use what we just came up with, except stick a subtraction sign between them. So I'm going to go jump to the second line of f of x plus g of x, and I'm going to write it like this: x squared plus 3x over x times x minus 4. And then I'm just going to switch out the operation and call it minus now, x squared minus 3x minus 4 over x times x minus 4. Now with subtraction, you have to be really careful about the way that you combine the terms together. The subtraction applies to everything in the numerator of that second fraction. So I'll start with x squared minus x squared, which goes away. Then I have to look at 3x minus negative 3x. That's going to combine to actually give me positive 6x. And then for the constant, I have to think about the fact that I'm subtracting a negative 4, which is going to make it become positive 4. So I would have 6x plus 4 all divided by x times x minus 4. And that would be an acceptable place to leave f of x minus g of x. Moving on to multiplication. For multiplication, we're going to have f of x times g of x. This is going to be x plus 3 over x minus 4 times x plus 1 over x. So when I'm multiplying these two fractions together, I'm just going to end up leaving the whole thing in factored form, and I'll just leave it as x plus 3 times x plus 1 all over x times x minus 4. So we'll just do that. The division, f of x divide by g of x. This is going to be x plus 3 over x minus 4, all divided by x plus 1 over x. And with division, we're going to turn this into a multiplication problem by keeping f of x as it is, but then I'm going to multiply by the reciprocal of g of x. So I'm going to end up multiplying by x over x plus 1. And then once I get it to a multiplication problem, then I can go back to what I did with multiplication. And I can just multiply across the top, calling it x times x plus 3, and then in the denominator, calling it x minus 4 times x plus 1. The last combination is a composition, f composed with g. That is going to be f composed with g of x. So that's going to be f of x plus 1 over x. So for the composition, I need to take everywhere that I see x in the f equation, and that would be in the numerator where it says x plus 3, in the denominator where it says x minus 4, and I'm going to have to plug in x plus 1 over x for each one of those x's. So it's going to look like this. X plus 1 over x plus 3 all over x plus 1 over x minus 4. So this creates a complex fraction, and we had a complex fraction also with f of x divided by g of x, but the difference here is that in the division problem you had just a single fraction divided by a single fraction, and so you can immediately go to that flip and multiply step. I can't immediately do the flip and multiply step because I don't just have a single fraction in the numerator or in the denominator. They are both a fraction plus a whole number or a fraction minus a whole number. So I need to figure out what this looks like as a single fraction in the top and bottom. Then I can go back to doing what we did with the division. So I'm going to treat 3 and 4 as fractions by making them both over 1, in which case I can then go and do a multiplication by x over x to get a common denominator. So this is now going to say x plus 1 over x plus 3x over x all divided by x plus 1 over x minus 4x over x. So now we'll have one fraction in the numerator. That'll be 4x plus 1 over x all divided by negative 3x plus 1 over x. So we're combining like terms there. And let's give ourselves a little more room. Now we'll do the whole flip and multiply. I'm going to leave 4x plus 1 over x, but I'm going to multiply by x over negative 3x plus 1. In which case, I have common factors. I have x's that are factors, not individual terms, but actual factors here, and I can cancel them across the multiplication and division, and that will result in 4x plus 1 over negative 3x plus 1. So that gets me all of the different equations that I need for my function definitions. But we also know that a domain is required in order to get the function definitions complete. So let's go back to f of x plus g of x, and let's work on that function definition first. So we're going to call that f plus g. Let me give a little separation here. So everything above the red line is our equation calculation. Everything below the red line will be where we put the function definitions, starting with f plus g. So the domain of f is all real numbers except for 4. The domain of g is all real numbers except for 0. When we create the combination using addition, subtraction, and multiplication, we are expected to take the two domain restrictions and combine them together. So that's going to result in the following domain: negative infinity to 0, union 0 to 4, union 4 to infinity. And that domain will map to other real numbers by the equation f plus g of x is equal to 2x squared minus 4 over x times x minus 4. So there's our function definition for f plus g. F minus g will start off exactly the same. In other words, it's going to have the same domain. So that is one of the nice things about these problems, is once you figure out the domain for f plus g, you will get to reuse that several times. And then we'll say by f minus g of x is equal to 6x plus 4 over x times x minus 4. Multiplication, f times g, or fg. Fg will also use this domain. So let me copy that down. That maps to real numbers, given by fg of x is equal to x plus 3 times x plus 1, all divided by x times x minus 4. So all three of those are going to have the exact same domain every time. But when we get to division, we are going to use this domain, and then we're going to include any other extra restrictions that come from the final equation. So for example, if I look at the final equation on the division, my denominator says x can't be 4 and x cannot be negative 1. Now I already have x can't be 4 because of the restriction on f. We have x can't be 0 because of the restriction on g, and now we have an extra restriction that x cannot be negative 1. This is because we're doing a division combination. So we're going to have to incorporate all three of those restrictions in our domain. So f divided by g colon negative infinity to negative 1, union negative 1 to 0, union 0 to 4, union 4 to infinity is the domain, and the domain maps to all real numbers by the equation f divided by g of x is equal to x times x plus 3 over x minus 4 times x plus 1. One more function definition to go, and that will be for the composition. F composed with g is the name. Now for the composition, we have to be a little more careful about how we come up with the domain. The domain restriction starts with the domain of the inside function. So g of x is our inside function here. That's what we start with the substitution. The restriction on g of x is that x is not allowed to be 0. But then we have to jump straight to the final equation and check to see if there are any restrictions with that. So the restriction on the final equation says that we have negative 3x plus 1 in the denominator. So if you set that equal to 0, negative 3x plus 1 equal to 0, you'll get negative 3x equals negative 1, so then x would have to equal positive 1/3. So that's the other restriction. We don't have to use the restriction for f, because when we substitute g into f, that restriction on f is what becomes x can't be 1/3. So we are using the f restriction it just isn't going to be represented by 4, it's now represented by 1/3. This is the nature of that composition having a substitution involved. So we're going to have two domain restrictions to write this with. So we'll have negative infinity to 0, union 0 to 1/3, union 1/3 to infinity. This is what we'll map to real numbers, given by the equation f composed with g of x is equal to 4x plus 1 over negative 3x plus 1. And all of these together represent the function definitions for f plus g, f minus g, f times g, f divided by g, and f composed with g.